by Davide, Gandolfi on CoRoT-32b.
Okay, thank you very much. I'm going to talk about CoRoT-32, which is the youngest aligned planet known so far. And let me first start. I would like to thank the entire Exoplanet science teams, because this is a joint effort. And I would like to thank also the mission CoRoT. Without all this, I mean, what you're going to see today would not be possible without CoRoT. Let me just give you some scientific background. Here you see the mass of known exoplanets, including also those detected by radial velocity, as a function of the semi-major axis. And there is this well-known cluster of objects which are piled up around a few orbital days around the star with a mass as comparable to Jupiter. And actually the first exoplanet belongs to this family. These are known hot Jupiters. And it was clearly understood that this object cannot form in situ, simply because you don't have the right condition to form a planet like this in the proto-planetary disk. But they actually come from the right side of the diagram, and they migrate inwards. What is not clear is how they do migrate. What has been proposed at the beginning is that a planet like an hot Jupiter formed beyond the snow lines, when volatiles like methane, ammonia, water can condense. They form before the disk dissipate, and then they migrate inwards through tidal interaction with the disk until they reach the inner region of the system. And this would account for planets, would explain planets in a nicely circular orbit, and because the migration is a smooth migration and won't change the angle between the orbital angular moment, the angular moment of the orbit and the stellar spin axis. So you expect it to have an aligned system. And indeed, the first planets with which you measure this quantity turn out to be aligned. But then there were found planets were misaligned. And it was clear that this kind of migration didn't work. So how to explain that? It was proposed that those planets undergoing, for example, gravitational scattering with a third planar or Kozai mechanism that will lead to the formation of a planet in an eccentric orbit and strongly misaligned. So is it clear that we have two major different planet migration scenarios which has been proposed? The first one is migration inside the disk with the formation of an aligned system on a nearly circular orbit, and gravitational scattering that leads to the formation of a random distribution of the spin orbit angle. How, first of all, we measure this? Well, we measure through the detection of the Rosetta-McLaughlin effect, which is this radial velocity anomaly that you observe during a transit, which is caused by the fact that the planet, according to how the orbit is oriented with respect to the stellar spin axis, will be crossing more the red or the blue shifted part hemisphere of the star, and the shape of this curve will change. And from the shape of this curve, you can measure the inclination of the two spin. Now, this has been done for about 60 hot Jupiters, and what was first spotted by Josh Wynn is that there seems to be a lack of aligned system for temperature hotter than 6,250 K, while for cold object you have mostly aligned system. How this was explained is that if you assume that planet migrates through gravitational scattering, and then the obliquity is dumped down by tidal interaction with the star. Tides are more efficient around cold stars than hot stars. So in this case, a planet that starts with an orbit that is misaligned the angle of the spin orbit angle will go down faster than what happened on the right side of the diagram, simply because tides are more effective here than there. But there is an issue. First of all, there is a clear lack of object on the right side of the diagram. So in my feeling is that we are dealing still with low number statistics. And the second thing is this holy tidal interaction time scale, which depends on the tidal quality factor, which is a quantity we don't really know for stars. It could change within the 3 order of magnitudes. And we don't even know the tidal interaction, the tidal parameter of exoplanets. The only planet for which we know this is Jupiter. So we are doing a certain number of assumptions. So what we would like to have is a planet on the right side of the diagram where you can neglect tides. And here is CoRoT-32 for you. is an hot Jupiter-like planet around a rapidly rotating F4 star on a 20-day orbit. The stars show activity from which we derive a rotational period of 0.8 days. Here you see the transit-like curve folded. It's a long duration transit. Here you see the parameter of the star, and as expected, the Vicenai is really high. It's about 80 kilometers a second. But what was really interesting is that when we put the star on the HR diagram, we found a solution that is either a Premann sequence solution or a post-zero age-main sequence solution. And we were wondering which one of the two. And then we found lithium. We found a large amount of lithium in the star. You might say, well, the star is hot because it's 6,750 K, and lithium cannot use as a youth indicator. It's not completely true, because look at this. You have the lithium abundance as a function of effective temperature of star for the year this, 700 million years. You can clearly see that the right side lithium is depleted as expected, because convective lava can bring the lithium down. But it's also happening in a really narrow temperature range, which is exactly where CoRoT-32 is falling, where this is called lithium D, is well known, and still lithium can be used as a youth indicator. So if we find the lithium, this means that the star has to be young, and we found it almost as value corresponding to the meteoritic value. So here are the parameters we derived for CoRoT-32, and we know the stars are born in cluster, and we were wondering, is there any other cluster projected where CoRoT-32 is located? So we got age, extinction, distance, systemic radial velocity, proper motion. We found that there is this nice cluster, and you see 22, 32, and these are the parameters. They nicely agree with each other. So this makes CoRoT-32 a clear member of a young cluster which has an age of about 25 million years. We performed photometric follow-up to better constrain the parameters, the orbit, and the mid-transit point. We did an intensive radial velocity follow-up to derive the mass using HARPS and FIES NOT across basically 2.5 winter seasons. And we believe we got the mass of the planets, though we have about 1 sigma detection. It's clearly an hot Jupiter. And we decided to try to measure the spin orbitability of the system. But we are dealing with a rapid rotator, so how do you do that? Well, the Rosetta-McLaughlin effect is actually seen as a moving bump across the stellar line profile, because a planet which is crossing in front of a star is acting like a spot. So if you can resolve the spectral lines profile, you will see a moving bump moving across the stellar line profile. What you do, you spot your bump, you subtract what is the expected line profile without the bump, you get this nice thing, so you just pile it up as a function of time. So you got here velocity or wavelengths, if you want, as a function of time, and you got this. This is the Doppler imaging map of CoRoT-32, and you can clearly see, okay, you have first contact, transit midpoint, fourth contact, and you can clearly see that we detect the bump moving across the stellar line profile. Interesting, the bump disappears at the expected contact, at fourth contact, and most important, the planet at the midpoint of transit is at the barycentric velocity of the line, which means the planet is crossing in front of the spin axis of the star. If you consider this and you combine it with the fact that the impact parameter is not zero, you got necessarily the only solution is that the orbit has to be aligned. Say so, let's go back in our previous plot and we put CoRoT-32, and it seems to be a clear outlier. And so we found this planet on this planet which has an age of 25 million years, which is aligned, and it's not only aligned on the plane of the sky, but it's also aligned along the line of sight, because we know the Vicenai, we know the rotation period of the star, we know the radius, we can measure the inclination of the axis with respect to the line of sight, and this is 90 degrees, which is equal to the inclination of the planet, because we have a transiting planet, which means that the system is three-dimensionally aligned. Now, let's talk about tidal interaction timescale. Well, the planet is in a 0.16 astronomical units. If you consider all the range of possible of the tidal quality factor, you find always that the tidal interaction timescale is longer than the age of the universe. Which means what we measure today is the primordial alignment of the system. Which means most likely this planet migrates through smooth interaction with the disk, reaching the inner region. Now, this is not the end of the story. Something that I consider really interesting. So, there are two scenarios in star-planet interaction. The first one is the planet migrate and reach the inner region of the system. It reach the so-called inner wall, which is co-rotating with at the same rotation period of the star. Well, so basically, the inner wall is rotating at the same rate as the star because they are frozen by, they are locked by the magnetic field of the star. In this case, so you have that the planet is in a one-to-one resonance with the inner disk of the inner wall or with the star rotation. So P-ROT, so the rotation period of the star was once equal to 20 days. Second scenario, the planet can actually migrate inside the cavity and reach the 2-to-1 near resonance motion. This means that the rotation period of the stars when this happened was roughly twice the orbital period of the planet. We have a 25 million years old system, so the star didn't have time to lose angular momentum through wind. Secondly, as I said before, tidal interaction timescale are really long, so the angular momentum of the star has not been altered by the planet. So I can apply the conservation law of angular momentum. I know the rotation period of the star today, I know the radius of the star today, I know its mass. I know what was the rotation period of the star when the planet reached the inner region. I know the mass, which has been preserved roughly. What is, I don't know is the radius. I can compute the radius. And if I do this, this is the evolutionary track of CoRoT-32. So you have the radius of the star as a function of temperature. Here is the current position of the system. You simply go back in time and say, when did the star had the radius I found assuming 1-to-1 near motion resonance? And what was the radius when I assumed 2-to-1 near motion resonance? And I found this value. You put down isocronous, and you find that the system was already formed at least at 0.6 million years age, which is what theoreticians are saying to us. You can form a Jupiter-like planet migrated really quickly. So we are basically proving for the first time that this is going on. And so I leave you with these conclusions. CoRoT-32 is a milestone discovery because it's the youngest aligned system known so far. Most likely, we found that the system is aligned, and this means that most likely the planet migrates through interaction with the disk rather than gravitational scattering. Is a clear exception to this rule saying that hot Jupiters around hot stars are usually misaligned. And we have proved for the first time that the formation and migration timescale has to be at least 0.5 million years, or about 0.5 million years. That's it. I'm in time.
Eric, first question.
Thank you. Could you show us the light curve once again, please?
Yep. Yeah.
Yes, this one. Because, of course, it would be a bit difficult to say it straight ahead, but I mean, with the star in this position, this kind of light curve looks very much like, you mentioned activity or...
Yeah, you mean pulsation.
Yeah. Like
that's
maybe you have checked.
No, that's been an issue we have been discussing.
Does QT pulsator really show this kind of
I might have
light curves? And you are
have
just
some extra slides.
at the corner of the instability
Oh,
strip.
you see better?
Yeah.
So I just removed the transit. And if you want, here is the periodogram of the light curve.
Yes, but
So we
no.
believe that this is
It should be higher.
this is the rotation
Yeah,
of the
yeah,
star,
okay.
and these are the ones.
Yes, no, but I would be looking much higher.
No, there is nothing.
Nothing.
I did it. And we have a sampling at 32 seconds because the star is bright, it's 11.5, and there is nothing.
Okay, so not for delta square
No.
T, but maybe for gamma.
And also, we have free color light curves.
Yeah.
And when you look at, you clearly see that the amplitude of the variation increase with decreasing wavelengths that we would expect when you have spots because the contrast increase. But this is also something that happened on pulsation, I know. I'm not an expert on pulsation.
I don't know,
But it's nicely matching what the contrast you get from different colors is nicely matching the contrast you would expect for the temperature of the spot on the star.
yeah, sure. I see
And
your
then-
argument in favor of the spot are good. I was just thinking that maybe it would be worth to have a look from a more stellar point of view.
There is nothing. I would have loved to see some other frequencies, higher frequencies, but there's nothing.
Thanks.
Okay.
So I understand that the transit duration is quite long, right? So it's a substantial part of the modulation, the orbital modulation. So I wonder if this can interfere
It
with
does.
your
It does.
estimation of the depth of the transit.
I applied two maths. Okay, if you look at the single transit, I'm sorry I don't have any plots here. You can clearly see that during the transit you see a modulation of the transit is not nicely as I showed you before, because in the meanwhile the transit is going on, the spots are also moving. I applied two kind of filtering. I did a first trial with Fourier filtering, so I just subtract sinus and cosine function. And then I did another one which was a spot modeling using a neutral answer code to get rid of the stellar variability in the out of transit light curve and then fit it into the transit, or basically subtract it, or to get rid of this effect. And the residuals are compatible with what I get from the errors, from the scatter of the error of the data points.
Okay, next question.
Yes, just one comment is that 0.25 million year, your star may still be accreting. This kind of new idea with this new paradigm with episodic accretion.
You mean with the second scenario?
Yeah.
With this one?
This one, and therefore angular momentum, the accreting matter will transfer angular momentum to the star, and therefore you cannot assume constant angular momentum. So that may be a difficulty with this scenario.
That would be a lower limit because, well, the planet might actually have will stop somewhere in between, right? Which would move this point up to here somewhere, right? Down here. So this is really the limit. If the planet really stopped at the 2 to 1 mean motion resonance.
I have a similar question, Isabel. I think during the first million years of lifetime of the star, during the first million years of the lifetime of the star, the angular momentum of the star really is regulated by accretion, balancing accretion, all these complicated things. So I was just wondering how you model this. It's not angular momentum conservation. I think I agree with Isabel completely. So I'm not sure how you actually get this.
I assume that actually what the planet and the star is gaining at or looking at the angular momentum of the particle that matter to actually can be injected, because basically the star is already full. There are only column accretion coming from this into the star, but most of the matter is already you believe it's a fraction of the dark fraction?
This new idea. Sorry. Yeah, it could be actually, and yeah. Yeah, but within less than 1 million years, we think now that accretion is not a steady process anymore, and therefore the star may accrete through burst of accretion, which may still happen actually at 0.5 million years, for example. So Donglai is perfectly true that during the first million year, you may still the angular momentum of the star may still be driven by accretion process, and then you have flows, etc. Therefore, you can gain, and well, the star can gain or lose angular momentum. So constant angular momentum may not really be. It's the very basic, simple assumptions. Even yeah. I don't see how, yeah. But we can discuss.
Well, I think this needs an offline discussion here. One last question from Arif Ophir.
Hi, can you go back to the impact parameter?
Say it again?
Fit? Impact parameter fit.
The one here?
Yeah, you said it's 0.3. Do you remember by accident the error bar to the lower side? Because impact parameters are very difficult to estimate on the downward side.
I don't remember by heart, but it's small. I mean, it doesn't bring the planet on the equator.
Because your assumption of alignment is critically dependent on this
Not really. Look at this, for example. Well, of course, when you make the model, this is the vicinity of the star, right? The red line here. And you see that actually the planet disappeared before, which means that is because it's not transiting on top of the equator, but it's transiting a chord which has a projected velocity which is smaller than the equator velocity. Of course, there is noise. Of course, the sampling. I mean, I'm integrating. I have integrated almost 20 minutes exposure each of these each of these map. But I don't remember how the number. But B is not that. The error on B is not large.
Okay, I think we have to get to the next talk.